The Best of Our Knowledge explores topics on learning, education, and research. Coming up, scientists have discovered a distant planet that resembles a lemon. And while studying a mysterious cloud of hot dust 70 light years away, researchers have found an unusual star. I'm Lucas Willard, host of The Best of Our Knowledge. You're listening to The Best of Our Knowledge. I'm Lucas Willard. Have you ever thought a planet could resemble a fruit? Scientists have discovered a planet shaped like a lemon, and its shape is caused by a strong gravitational pull from a nearby star. Discovered using the James Webb Space Telescope, the planet, officially named PSR J2322-2650b, orbits its star in less than 8 hours. Madeline Reynolds spoke with Maya Belesne, a PhD candidate at Stanford University and a co-author of the discovery published in the Astrophysical Journal Letters about her team's research.
This star is really weird because it's only 10 kilometers in radius. It's the size of a city. It's really small for a star, but it weighs 2 times the mass of our own sun. So it's really one of the densest objects in the universe. And because of this, it has this really extreme gravitational pull that's kind of pulling the nose of the planet towards it. So it's like, like the planet is kind of like a ball of Play-Doh, and the gravity is just kind of sucking the front of it into this lemon-like shape.
So can you just talk about this star, which is essentially this planet's sun? And in the research, it's described as bizarre. So I'm just wondering why it's bizarre.
Yeah, so this star is actually a dead star. It is the remnant core of a star that has exploded. So there are, a lot of different types of stars in our universe, and we usually measure them in solar masses. So when we say a certain amount of solar masses, we mean that times the mass of the sun. And so when stars that are 8 to 20 solar masses explode at the end of their lives, they leave behind this extremely dense core of just neutrons, basically. The gravitational pull that's kind of causing this whole thing to collapse is so strong that there's no more atoms in it. It's just neutrons. It's just what was at the center of all these atoms. So it's kind of really on the edge of collapsing into nothing, into a black hole. And that's an open research question right now, is how dense can one of these neutron stars get? Other interesting things about these is a lot of times, I said they die in this violent explosion, but they will have a binary companion pretty often. And this binary companion can actually survive that explosion, meaning that if something was orbiting around it, like this planet that we're discussing, that will actually survive. And so what you're left with is this really dense core and something orbiting around it. And as that partner continues to orbit around it, it can actually spill some mass over onto the neutron star that will cause the neutron star to start spinning extremely, extremely rapidly. And this is why we call them pulsars, because they have these kind of beams that come out on each side, and they look like lighthouses in space, and they kind of pulse around. This particular one actually spins 300 times per second. So it's like really crazy. To our ears, that frequency would be like a continuous sound. We wouldn't even recognize like discrete pulsations if we were to look at this. And so you have this object, this neutron star that's spinning really rapidly. I mentioned it has these beams coming out on either side, but these beams on the sides and other light that's coming out of it is all completely invisible to the James Webb Space Telescope. It's a completely different wavelength. James Webb sees infrared wavelengths, which is a little bit longer than what our eyes can see. And the particles coming from these neutron stars are way higher energy than that. So essentially, what we're seeing, like when we take a measurement, is just a lemon-shaped planet orbiting around something that the camera can't see.
So along with this bizarre pulsar star, something else that was deemed in the article as also being something nobody has seen before is the atmosphere surrounding this planet. I mean, what are the characteristics of this atmosphere and why is it something that has never been seen before?
We've been learning a lot about exoplanet atmospheres. We see it in the news all the time that water was detected on an exoplanet. People are finding planets that are similar to our Earth. People are finding similar planets to Jupiter, like gas giants. And they find all sorts of molecules on these. I mentioned water, carbon monoxide, carbon dioxide are common ones. But the interesting thing here is the fact that we're seeing molecular carbon. And by that I mean we're seeing carbon atoms binding to each other. Usually for planets, that's not possible because carbon atoms like to bind with everything else before they like to bind to each other. So the fact that we're seeing C2, like a molecule with two carbon atoms or a molecule with three carbon atoms, means that there's really nothing else there. And that's unique because if this thing is a planet, planets form from the debris around stars. And the debris around stars is never just carbon, there's a lot of other things there. So planet formation models fail to explain how we're seeing molecular carbon at the surface. This is also true for the evolution scenario where this lemon-shaped planet is actually a really old star. Stars form with nuclear processes, and nuclear processes do not make carbon by itself. So it's a really big mystery. It should be important to note that, I'm not saying this entire planet is just made out of carbon, because if that was true, its center would be 500,000 degrees, and we know it's not that hot. 500,000 degrees is a lot. So the kind of leading theory here is that we have some carbon that ended up on the surface, or at least in the layers that we can see with James Webb, but the whole thing is primarily made out of helium. And helium is a very inert kind of atom. It doesn't like to bind with anything. So we wouldn't really be able to see that. We're continuing to work on this project and working on detecting helium to see if this idea is true. But so what we're talking about here is, an object that has the same radius and the same density as a gas giant like planet, but it has a composition that no planet formation model can explain. We know that at the surface, we're seeing molecular carbon, but we don't know how much helium there is, and we also don't know what's in the middle of it.
The big question seems to be this: how it came to be. Like how did it form? And in the article, I don't think there's a definite answer, but there is a theory as to what system it could be a part of, possibly, which could provide answers. So I'd love for you to talk about that.
Yeah, so we're a team of exoplanet scientists and pulsar scientists, and we initially thought this object would be a member of this class of systems that we call black widows. Black widows are systems where we have a pulsar just like this one and a very low mass companion that orbits around it. And we have example systems where the hydrogen has been completely stripped off from the black widows. We actually call them black widows because it's like what the spiders do. Like they eat their companion, and you have one very massive one, and then the male is really tiny. And so for these really evolved black widow systems, this mass transfer process that I talked about, where the mass from the companion it leaks onto the pulsar essentially over a long period of time. That will deplete a lot of the hydrogen, and you're left with these things that are dominated by helium or heavier elements. And so we would naturally want to say that this is part of that evolution, but it's the very extreme end of it. Um, but again, it's the ratio of elements that don't make sense. You have 10,000 times as much carbon as nitrogen and 100 times as much oxygen or as much carbon as oxygen. And that's not something we see in any other black widows. Usual black widows also tend to be way denser than this object that we see. And so that's why we're in this remnant star or planet debate about this system. There are systems where you have like a white dwarf that orbits a pulsar. White dwarfs, there's different types of them. There's types called helium white dwarfs that are primarily helium. There's also carbon white dwarfs. But the thing about all of these is they do have all the elements that the nuclear processes create. So they do have nitrogen and oxygen as well. They're just kind of in the middle. And so one idea is that, you know, you have all the elements, but as this star remnant cools down, the heavier ones, oxygen and nitrogen, kind of crystallize in the middle, and that allows some of the carbon to float to the surface. And that can be plausible. It's just something that's never been observed before. And so we don't really have a model that we can test with this. But it is something that has been predicted, I think. So it is possible that you have some event or, you know, this Black Widow, we took a snapshot of it at exactly the right moment to see when the carbon is starting to segregate from the other elements. It's just that it's such a particular moment that we don't, it's in science, you know, we don't really like to say like that something was really fine-tuned and it just happened to be this way at exactly this time because it's never been observed before. So there isn't a satisfying story for this. Another possibility is that two specific types of stars collided to form this one, and then this resulting object is what was left orbiting the pulsar. But again, the fact that you have to invoke more than three stars in this scenario is not it's not satisfying, and we don't think that's the real story. And so I think if we were able to continue to get more measurements about it and understand really what fraction of it is made out of helium, then we can actually pin the story down a little bit better.
Maya Belesne is a PhD candidate at Stanford University. Her research is published in the Astrophysical Journal Letters. She spoke with the best of our knowledge's Madeline Reynolds. And now for an astronomical mystery about 70 light years from Earth. The star known as Kappa Tucanae is surrounded by a curious hot dust. While studying this dust, researchers at the University of Arizona were surprised to find a companion star that moves through the same region as the dust. I spoke with Thomas Stuber, a postdoctoral researcher at the Steward Observatory, about his team's discovery and what it could mean for space exploration.
Kappa Tucanae. That's a star system in the southern sky. So from the southern hemisphere, you can see it with your naked eye. It's a relatively close system, 70 light years away from us. The star itself is like 20 years ago was not very much known very well. It was nothing special. There are a lot of stars in the sky. The system itself was known to be a binary system. So two stars quite some distance away from each other, orbiting around each other. And also the system was known to be part of a larger constellation, like back then a quadruple system, so four stars, so the two stars, and then at some distance away, even more far away, two other stars. But that's fairly common among stars. And then this star was observed with high spatial resolution interferometers. And then it was found that it was most likely, so that the primary star, Kappa Tucanae A, we call them A and B, and we just use letters to address them, was found to host a distribution of what we call hot exozodiacal dust. This is dust that is very, very close to a star, so closer than the Earth is to the sun, roughly, and thereby is very hot. It has temperatures of 1,000 degrees Fahrenheit or more, twice that, up to the sublimation temperature of those dust grains where they vaporize. And then this, prompted this star to be observed multiple times later on.
So tell me about this dust. When you're looking through equipment at a star that's very, very far away, Does this dust actually create a problem for astronomers when, looking and observing at distant stars?
So it can create problems, but in a different way. So this dust is really, so this belongs to the circumstellar dust. So this dust inhabits the region really around the star. So because this star is 70 light years away from us, that's very far, and we find the dust really being very closely around the star. So we look at something like our solar system that is very far away from us. So because also in our solar system we have dust that lives around the sun, and this is a very thin, very tenuous dust distribution. And usually we don't care about it. In many respects. So we can see it via the zodiacal light, for instance. So the zodiacal light is shimmer of light that you can see, for instance, after sunset or before dawn. And this is scattered light, so light from the sun that gets scattered off these dust grains towards us, and so we can see those dust. But it's really a tenuous distribution. So if we now place this solar system dust around a different star, we can also see it, but it's not in that way in the way, because we mostly look through it, but the dust itself adds some emission because it's hot. It has a temperature, so it emits, and we can see that. So it's really, so imagine, yeah, you have the sun, you have the earth. So for this particular type of dust, you have the sun, you have the earth, and like co-located with the earth and closer to the sun, there's a tenuous distribution of dust, and that glows. And this is what we are observing, and that what we found around Kapatuk. And the difference, so Kapatuk is not the only star that has this phenomenon, but the difference is, compared to the solar system, this dust is orders of magnitude 1,000 times brighter. It's still a thin dust distribution, but it's much brighter than in the solar system.
Judging what we know of what we can detect, you say, well, that dust doesn't really quite make sense as to why it's so hot. So you and your team took a closer look. As I understand, you used multiple telescopes to observe this cloud that's so far away. And along the way, what did you discover when taking, a repeated look at this object? Something happened, right?
So yeah, we used what we use an observational technique called interferometry to do our observations, because the star is far away, and this dust distribution is very close to the star, and the star itself is super bright. So compared to everything else, it's just bright source. So we need a very high spatial resolution with our telescopes to distinguish this star from this faint dust. So this is where we use interferometry to do that. And then we did repeated observations, new observations in 2022, 23, 24, with the intention to study how this dust behaves over time. Does it get brighter? Does it get fainter, for instance? And then what we found was that there's actually not only the dust, but there's a third star, an additional star. So earlier it's a binary, but the secondary star is far away, so we don't care about that. But then we found a third star in there that is super close to the host star. So we found that, and with our repeated observations, we were able to constrain the orbit of that third star around the primary. And this was, so first of all, finding this star was a huge surprise, because the system has been observed before, and there were no signs of a companion. So a companion star. So we were first very confused what our data showed us. Like, this looks like a star, but it wasn't there before. What did something go wrong? And then, like with careful analysis, and we found that everything made sense. But we had a companion star, but that this companion star was on a highly elliptical orbit around the primary star. So in the solar system, we don't have a secondary star. We only have planets, but they orbit almost on circular orbits. Like the Earth's orbit around the sun it's very close to a real circle. But it's also possible that these orbits are elliptical, and this star is on a highly elliptical orbit. So it really comes very close to the primary star and then retreats far out into the system. So, and at its closest approach, it's like 0.3 time, so it's 30% the times of the distance from the Earth to the Sun. That's even closer to the star than Mercury in our solar system is to the Sun. So really, really close. And then it retreats to like 8 times the distance of the Earth. So goes far out into the system. And this is why it was missed before, because the previous observations were done when the companion was far away. So it fell outside our field of view. So we didn't see it. And now we catched it. And this changes the whole view of the system.
Is there a connection, do you believe, between this companion star and this hot dust that's in this star system?
Well, that's what we're thinking. Or let's say that's the new hypothesis. Because explaining this hot dust has proven to be difficult. So it was detected for the first time in 2006, so almost 20 years ago. So, but on a, like a, it's by that way, it's still a fairly new phenomenon, but by now it has been known for 20 years. And explaining this is, yeah, challenging because this hot dust, super close to the star, it has high temperatures, temperatures going up to the sublimation temperatures of those dust. So this dust should vaporize very, very quickly. On the one hand, or on the other hand, these dust grains are very, very small, so sub-micrometer in size. So for comparison, a human hair has it's like dozens or even hundreds of micrometer in thickness. So these are very, very tiny, tiny dust grains, comparable to smoke from a fire, perhaps. And these dust feel the radiation pressure from the photons that coming from the primary star very much. So the light from this central star is able to push away these tiny, tiny dust grains out of the system. And both this vaporization and this being blown out by the radiation pressure should remove, at least around the brighter of those stars, should remove those dust grains in a matter of days or weeks. But we find this dust in high amounts around several stars, repeatedly. So there either has to be something that replenishes this dust super, super rapidly on a daily basis, basically, or that probably in combination to that, there's something that traps the dust there that either prevents it from being blown out or extends its lifetime against vaporization. And now, so what could be a delivery mechanism of this? This could be exocomets. So we like comets in our solar system, just around other stars. That's what we call exocomets for exosolar comets. They could fly in and deposit that dust there. But those exocomets have to stem from somewhere, so some outer reservoir of comets or asteroids, comets, which we call planetesimals for small planets. And those have to be thrown onto orbits leading so close to the star. And this is where this companion star comes in, because it causes very interesting gravitational dynamics in that system, because it comes so close to the star and then retreats far out into the system. And this could potentially cause such exocomets fly in there. So this is really so the exocomet idea is not new, but hasn't worked very well so far. But this new system could be a real laboratory for us where we could observe this happening, because we now see those two stars. The companion star has a big advantage over exoplanets because exoplanets are very, very faint, and usually we don't see them. But this star is bright. We know where it is. We know its orbit, so we can dynamically investigate this rather easily. So we have now, and the time scale is relatively short. So within about 8 years, this companion star completes an orbit. So on human timescales, we can actually see this changing. So we have a natural laboratory that we can now further study further, monitor, and see, for instance, does this orbital period of that star, it's coming close to the primary star and getting away from it, correlates with the behavior of the dust getting brighter, the dust getting fainter. So this is what we really hope to get from the system. And that's why we're really excited from that.
Well, Thomas, thank you so much for taking the time. I appreciate it. Is there anything else that you'd like to mention about this study or what's coming next for you in your research?
So what's coming next? Well, we talked about a lot about like what this study triggers regarding new hypotheses, new tests, new thinking. But what it also triggers is that we have now this system where we have had hot exocycle dust and now found a companion that we missed. And this actually might have happened around other stars as well. And what we now want to do is revisit those systems with dedicated observational programs that are at least very, very unlikely to miss any star there. And in most instances, we can really for sure determine like, is there a companion star or not? And so we want to revisit those systems because this might change the detection statistics, which are also very important information when assessing a phenomenon. And this will also be proof important for NASA's upcoming Habitable Worlds Observatory. So this is the new NASA flagship mission that is being built currently and is foreseen to launch in the 2040s. And this Habitable Worlds Observatory, or HWO, will be designed to detect an Earth sibling and doing high contrast searches for such exo-Earths. And there the hot dust might cause problems. So we need to really, until then, figure out what this hot dust, how it behaves, around which stars it lives. Does it change over time? Is it a common phenomenon around every star, but just happening every so and so many years? Or is it a phenomenon only appearing around certain stars? Such things are what we're currently working on. And there also the companion star thing comes into play, because if you want to detect an exo-Earth, you want to look at a system where a star swings through that region every 8 years, because that makes it unlikely to find an exo-Earth or an exo-Earth being there, and also generally challenges your observations. So yeah, we have a lot on our plate in this investigating this phenomenon, but it's also exciting.
Thomas Stuber is a postdoctoral researcher at the University of Arizona's Steward Observatory. This has been The Best of Our Knowledge, episode 1839. The Best of Our Knowledge is a national production of WAMC, Northeast Public Radio. Thanks to associate producer Madeline Reynolds. The latest on all National Productions programs via the Airwaves newsletter and our flagship station's website, WAMC.org. Until next time, I'm Lucas Willard.